And in case we lost almost all of that, there's the math from the problem we worked out. And that relates to master set 22, problem some 8. That. There you go, 8, and that's related to 13 over there. Let's just recap a little bit. We started out with Coulomb's law, which eventually evolved through definitions in math, and that if I look at the electric flux through a closed surface, that's going to be equal to whatever enclosed charge there is over epsilon sub 9. So there's free space other than the charge. This is Gauss's law of electricity. With magnetic fields, whatever flows in flows out, and it's addressed in one of the videos, but not a whole lot of time spent on it. If I have some sort of Gaussian surface, if I have some three-dimensional surface, whatever magnetic field I have going into it is the same as the magnetic field coming out of it. Unlike with charge, we're going to have a single charge. I can't have a single pole of a magnet, and so that's going to be equal to 0. And so this is Gauss's law of magnetism. If we look at if I have a current flowing through a wire here, I have a magnetic field that's generated by it. The magnetic field is coming out of the board up here and into the board down here in a circular path. And the strength of the magnetic field U naught I over 2 pi r. Generalizing it, multiply both sides by 2 pi r, and presumably you've seen this in the video already, times b is equal to mu naught I. This is just the circumference of that circle, and so if I imagine that sort of shift views around here, this is my current here going into the board, it creates a magnetic field going clockwise. This distance here is r. That the magnetic field all along here adds up to mu naught times I. And this I is enclosed by that loop. So we can generalize it as in, I take the magnetic field at this point, plus the magnetic field at that point, plus the magnetic field at that point, times however long that segment is. And so in essence, I'm just going to add up B dot delta L. So I just break this up into a whole bunch of tiny little segments and do B times that around a closed loop. And that's going to end up being U naught times I enclosed. So the first two, when I wrote out the shorthand notation of the electric flux, that's just the sum of the electric field times the area around some closed surface. This is the magnetic field times the area around some closed surface. And so now I've got B times delta L over a closed loop is equal to mu naught I. This is Ampere's law. And so there seems to be some symmetry here. We know that there's a relationship between an electric field and magnetic field. I have electric field times this area, magnetic field times the area, magnetic field times the length. Seems like I should have an electric field times the length also. So if I looked at the electric field times the length, what is it? In come Faraday and Lentz. It was generally referred to as Faraday's law, but I think Lentz deserves more credit than that. So both textbooks will call it Faraday's law. I think it probably should be called Faraday-Lentz's law, or Faraday's-Lentz's. And my understanding of the relationship here is that Faraday actually was the first one to figure it out conceptually. Lentz is the one who did the math into it. All right, so here's the experiment. I have an ammeter here, so it's something that's going to measure current. And it's hooked up to a wire. Beside it, I have another wire with a power supply attached to it, and a switch. I don't think I can erase, well, so I can erase just part of it. All right. What Faraday noticed is that when he closed the switch, the needle here would twitch. The twitch would go back to 0. When he opened the switch, the needle would twitch in the other direction and then come back to 0. What he ultimately figured out was that the electric current that was created here, when I turn on the switch, I go from an electric current of 0 to something. That electric current was changing the magnetic field inside the circle here, or inside this loop over here, and it was the change in that magnetic field in this area that was causing current to show up in the second wire, known as an induced current. You play around with it some. You can play around with the shape of this and the locations of that, and eventually figure out it's not the magnetic field per se, it's the magnetic flux, and more specifically, it's how the magnetic flux changes. So Faraday recognized that the current is somehow related to the change in the magnetic flux with respect to time. If I have a current flowing here, that means I've got a potential difference. Current requires a potential difference in order for charges to flow. And if we just crudely look at the stuff from the capacitors, that the potential difference is equal to the electric field times the distance. We can hopefully take the leap that there's some relationship between the electric field and the distance that the electric field is traveling around. And ultimately it ends up with the electric field times this length as I go around some loop is going to be equal to the negative change in the magnetic flux with respect to time. And this is Faraday-Lentz's law. So let's do a quick little study here. I I've got a magnetic field coming out of the board. And I have it basically contained. So no, this magnetic field I've kept inside this small little column here. I take a loop of wire and I move the loop of wire into it. So so what I'm concerned about is what is the magnetic flux through this? So before it gets into here, what's the magnetic flux coming through here? Do we need to do a quick review of what magnetic flux is? You remember what electric flux is? Okay, apparently there was a huge impact when we went over that before. Let's clear this. All right. Electric flux. That is the electric field times the area. It's a way of measuring sort of the strength of an electric field within a particular region. And that is a dot in between them. Magnetic flux, same thing, except with a D. So very simply, remember that the area vector is perpendicular to the surface. It is, for a closed surface, it always points outwards. For an open surface, it points one way or the other. So if I have a box here that is 3 meters by 2 meters, and I got a magnetic field coming through, perpendicular to it, and the magnetic field is 4 Tesla. My electric flux, well, first off, what's my area, what's the magnitude of my area vector?
Six.
Give me the whole thing.
6 meters squared.
Yeah, all right. So my magnitude of my area vector is 6 square meters. The direction is there are 2 answers.
Positive or negative K?
Which is the K hat? Okay, in or out, whichever direction we want to make it. It's basically a one-dimensional problem, so we can make that, let's make out positive. All right, so my area vector, positive 6 square meters. My magnetic field is positive 4 Tesla. And so I'm doing a dot product, so I'm multiplying parallel parts while they're parallel. So my magnetic flux would be 24 Tesla meters squared. Now, Tesla meter squared is too much for physicists to write. So that is 24 Webers. All right, so we've got, so it's just multiplying the magnetic field times the area it's going through. Oh, let's just make it slightly different. I have this thing partitioned, and so magnetic field on the left-hand side is 4 Tesla, and the right-hand side is 5 Tesla. The magnetic flux now, well, it's 4 times that area plus 5 times that area. That's supposed to be a capital T. So this would be, that's 3 meters squared, that's 3 meters squared, so it's 5 times 3 plus 4 times 3, 15 plus 12, 27 Tesla. I'm sorry, 1 Tesla meter squared. Questions on magnetic flux, because we're going to exploit our knowledge of it. All right, so back over here. When this loop of wire is not quite in my area here where the magnetic field is, what is the magnetic flux going through it?
Zero.
Yes, there's no magnetic field, so 0 times, I don't care what the area is. When it enters into it, let's assume that my area vector is that way. When it enters into it, my magnetic flux is not 0. The question is it increasing or decreasing? Oh, I'm willing to bet more than one of you knows the answer. Let's try this again. Magnetic flux here is what? When it enters, it'll be positive or negative.
Positive.
So, is the magnetic flux increasing or decreasing?
Increase.
There we go. As it leaves, will the magnetic flux increase or decrease?
Decrease.
Okay. It matters whether it's increasing or decreasing because that determines the direction of the current that is induced. If my magnetic flux changes through this wire, I will get a current. If I have a loop of wire with a current flowing this way, clockwise, which way will the magnetic field be in the middle? I'm getting fingers pointing in all sorts of directions here, not a general consensus. So I'm seeing 2 fingers in the right direction. Right being correct, in the correct direction. All right, so up here it's going out and in, so it's coming out, wrong way, coming out here and in here. What about at this point? Which way is it going on the inside?
Out.
So
Yes.
like that, so it's coming, yeah, your fingers will curl in the right direction there. I mean, it's going in over here, out over here. What about here? Okay. So, matter of fact, all the way around, the net current is, if my current's flowing clockwise, the magnetic field is in. If my current's flowing counterclockwise, the magnetic field is out. As my loop of wire here enters my magnetic field, the magnetic flux increases. As talked about with Faraday's law, I'm going to create a current in this. That current is either going to be clockwise or counterclockwise. if it's going clockwise, so as this enters, if my induced current is clockwise, it's gonna create a magnetic field in. If it's counterclockwise, it's gonna create a magnetic field that's coming out. So one of the magnetic fields that's induced could be in or it could be out. It's either gonna augment this magnetic field or it's going to counter it. Nature is not going to give you free energy. Let's think about the implications for the wrong answer. If this enters and it creates a counterclockwise current, so it comes in here, creates a counterclockwise current, that creates a magnetic field. So at this point right here, it's in. If it creates a counterclockwise current, that means it's going to create a magnetic field coming out. So it's already increasing my magnetic flux because of an increase in my magnetic flux. I think I just said the same thing twice. It's inducing a current because the magnetic flux is increasing. If it created a magnetic field in the same direction, that means it's going to increase even more. So if the current flew this way, went this way, we'd have run away because the magnetic flux, the change in the magnetic flux will create a current, which creates a even bigger change in the magnetic flux, which creates a current, and that current would just get bigger and bigger and bigger, free energy. We as a species would have died out long ago. They can be weaponized so easily. Actually, you don't even need that. If I just took if it augmented, all I had to do is take some piece of metal and drop it, and it would probably kill me. So current is not going to go that way. Current is going to be in the direction to minimize the change. So if my flux increases, it's going to create a current that tries to decrease it. So it's going to create a current, in this case clockwise, so that it creates a magnetic field opposing this. That is the power of this negative sign here.